Hello, my amazing Algebra Half students. This is Mrs. A, and I love math. And today we are on lesson 132 in our Addition 2 book and 120 in our Addition 3 book. And like I said, my granddaughter Hannah is on a roll. She is using this time where she's shut away with COVID-19 to finish up her math book. So maybe you're doing the same thing. We are talking about numerals and numbers. This is a big section. Larger than and greater than, pyramids, cones, and spheres. Lots in this lesson. So the very first thing, part A, is numerals and numbers. What is the difference between numerals and numbers? Well, a number is an idea. It's a concept. Okay, so this 1, 2, 3, 1, 2, 3, 1, 2, 3. The circles here have a concept of 3. The squares here, they kind of look like rectangles, don't they, have a concept of 3. And even though these are different shapes, they have a concept, I'm dividing them here with a line, a concept of 3. So the number 3 is the idea of 3. But we have numerals that are symbols for the idea of 3. So this is our symbol for the idea of 3. This was the ancient Roman symbol for the idea of 3. 3 sticks with bars across the top and the bottom. That was a Roman numeral 3, and this was a Arabic numeral 3, and that's what we use. And we've got numerical expressions with the value of 3. 30 divided by 10 is 3. 2 plus 1 is 3. And 15 divided by 5 is 3. So these are all numerical expressions. They're not numerals because numerals are just one item representing one idea, one symbol, but they're numerical expressions that all have the value of 3. So the big part of this section is just that the number is an idea, okay, and then the numeral is the symbol that represents that idea. And a numerical expression can have the same value of a certain number. Okay, so this numeral expresses 3. A numerical expression could express 3. But the number 3 is the idea of 3. So sometimes we do use them interchangeably, but your book just wants you to know the difference between the two. A lot of times we will use number when we really mean numeral, and it's not really such a big deal as long as we do understand there is a difference between the concept of 3 and the numeral that represents the concept of 3. The B portion of this lesson is larger than and greater than. Now, we have to be careful because words do not always mean the thing that we think they do. Bigger or larger in size is not the same as mathematically greater than. So here I have a 4 and a 2, and here I have a bigger 4 than the 2, and over here I have a bigger 2 than the 4. So here the 4 is larger, here the 2 is larger, because I'm talking about a physical size of the numeral. But greater than is a word mathematically used for a number that has a larger value than another number. So we would use greater than between number concepts. Okay, so the concept of 4 is greater than the concept of 2. And 4 is farther to the right on the number line, and 2 is farther to the left on the number line. So 4 is greater than 2, and 2 is less than 4. And we use greater than and less than to mean our number concepts are actually greater than or less than instead of the size of the numeral. So bigger and larger are a little bit more confusing. We might not know exactly what we're talking about. Are you talking about the number being bigger or the numeral being bigger? But we all understand mathematically that greater than means the number is farther to the right and has a higher number concept than the number that is on the left. So we're going to use greater than or less than instead of bigger than or larger than or smaller than, because we don't want to be confusing as to whether we're thinking of number or numeral. Okay, so the last section, part of this section is pyramids, cones, and spheres. And this part has a lot of cool pictures that are in your book, so I'm going to go there. Okay, so here is our book. There are formulas for the volumes of cones and pyramids and spheres, but formulas are hard to learn and easy to forget. Now let's look at these three figures here. We have a triangular pyramid. Now notice that the base is a triangle, and each one of the sides is also going to be a triangle, isn't it? We have a rectangular pyramid because the base is a rectangle. But notice that the sides are triangles because it's going up to a point. We have a circular cone, and a sphere is like a ball, like a beach ball. Okay, so we have those shapes that we need to learn. Okay, let's look at this part. There is an easy way to find volumes. The volume of a pyramid or a cone is exactly 1/3 the volume of the right solid that has the same base and the same height. The volume of a sphere is exactly 2/3 the volume of the right circular cylinder that has the same radius as the sphere and is just as tall as the sphere. So here we have a right prism here, and it has the same base as this triangular pyramid. It has the same base and it has the same height, but it is not coming up to one point. It is going straight up. So that would be the right solid that has the same base and height. And our rectangular pyramid, which is right there above, okay, the triangular pyramid, that is now enclosed in here, has 1/3 the volume of the right solid. So over here we have, again, a pyramid inside a right solid, and the solid, the rectangular prism here, has the same base and height as the, looking up there, rectangular pyramid above it that is now enclosed in it. And so the volume of the rectangular pyramid is 1/3 the volume of the right solid that exactly encloses the pyramid. So here we have a cone inside a cylinder, and the volume of the right solid cut in third, so 1/3 the volume of the right solid will give me the volume of the cone that's inside it, which you can see right above it, the circular cone. Okay, and then we have 2/3 the volume of the right solid is the volume of the sphere. So everything else was 1/3, but this one is 2/3. And you can look at it, the volume of the sphere is much, much more than the volume of each one of these other cones. So 2/3 the volume of the right cylinder is going to be the volume of the sphere that we see right there. So we can use those as formulas. It's much easier to find the volume of the cylinder and then just take 1/3 or 2/3 depending on what we're looking at. Here is an example problem, example number 1. The base of a triangular pyramid 4 meters high is the triangle shown. So this triangle here is the base of this triangular pyramid. Okay, find the volume of the pyramid. Dimensions are in meters. Oops, I pointed to the wrong figure. This is your triangular pyramid. This is your triangular prism. This is a solid. This is a right solid. This is the triangular prism that has this as its base. So now what we're going to do, since we know that this one is a pyramid, it's going to be 1/3 of the area of this one. Okay, so now we're going to find the area of, the volume of this figure, and then we're going to take 1/3 of that and we'll get the volume of this one. So remember, this is the same all the way up. So don't we just need to find the area of this figure and multiply by the height to find the volume of this figure? So what's the area of a triangle? 1/2 base times height. So this altogether, 6 times 3 would be 18, and half of that would be 9. And 9 times 4 would be 36. So this volume is 36 cubic meters. And then this was going to be 1/3 of that. So it's going to be 36 divided by 3, or 12 cubic meters. So I'll show you on our board. I decided to just go ahead and show you this one in the book because they had already drawn it for you. So the area of the base of the right solid is going to be the 18 divided by into 1/2, which is 1/2 of 18, which is 9. So the 9 meters squared is the area of the base, and then we multiply that by the height to get 36 meters cubed. So that's the volume of that right triangular prism. And then we're going to take the volume of the pyramid is 1/3 this volume. So 1/3 of 36 is 12 meters cubed. So let's go ahead and look at the pictures here, and then I'll go to the board. It says find the volume of a circular cone 4 centimeters high, whose radius is 10. So here's the base of the circular cone. Here would be the cylinder that encloses the circular cone. So we'll do this one on our whiteboard. Okay, so here's my best attempt at these pictures. This is the figure that we're trying to find the volume of. This is the base of this figure with a 10 centimeter radius. And this is a picture of the cylinder that would exactly enclose this. It has the same base as the cone does, and it has the same height as the cone does. So we know that the volume of this figure is exactly 1/3 the volume of this figure here. So all we have to do is find this volume, and then we're going to take 1/3 of it, and we'll have the volume that we desire. So let's think about, what is the volume of a cylinder? The volume of a circular cylinder, or any cylinder for that matter, because a cylinder is any figure that goes straight up. So we can have cylinders that have triangles as bases. We call those prisms. We could have cylinders that have rectangles as bases. We call those prisms too. Or we could have cylinders that have circular bases, and we usually call those circular cylinders. So we have a circular cylinder. It has this for the base. The volume of every cylinder is area of the base times the height. Area of the base times the height. That's it. So depending on what your base is, we will, since our base, the bottom of this cone, is a circle, we know that the area of a circle is pi r squared. Okay, so the area of this particular circle, since we have 10 centimeters as our radius would be 10 times 10 or 100 centimeters squared times pi. Okay, so we have 100 pi centimeters squared would be the area of this little circle. Okay, and then we have to multiply that area times the height to get the volume of this figure. Now, we're going to go ahead and use, instead of pi, we're going to use 3.14. And then when we multiply by 100, we have 3.14 and we multiply by 100, doesn't it move the decimal place 2 places to the right? That's easy multiplication, isn't it? So 1, 2. So the volume, the area of this is 314 square centimeters, and that's the area of the circle. So the volume here is going to be the 314 times the 4 cubic centimeters. So this one is 314 times the 4 cubic centimeters. So that's going to be centimeters cubed, and that will be the volume of this one. And we haven't done that math out yet, but the volume of this one, which is what we're really looking for, isn't it going to be 1/3 of this? So 1/3 of 314 times 4. So we're going to have 314 times 4 divided by 3 cubic centimeters will be the volume for this one. Okay, so now we have to go and do our math. So we're going to do 314 times 4 because that was this volume, and then we're going to divide it by 3 to get this volume. So here we go. This is our problem. 314 times 4 is 16 and 5 and 12, and then we've got to divide that by 3. So 1, 2, 5, 6 divided by 3 is going to go 4 with a 12, and then a 5 is going to go 1 with a 3, and a 2, and a 6 comes down, and 3 into 26 is going to go 8 times, which is a 24, with a 2 left over. A 2 is going to make this 2/3. So 418 and 2/3 cubic centimeters. And that is your first example. Let's get the big picture here again. We started by finding the area of the circular base. We multiplied that area by 4 to get the volume of the cylinder. We divided that volume by 3 to get the volume of the cone. And then when we did all of that work, we got the answer, which is 418 and 2/3. Yep, I got it right. Okay, so now we're going to find the volume of a sphere whose radius is 10 centimeters. So I'm just going to draw a ball because I cannot draw a sphere. But we know what a beach ball looks like. So this has got volume. Okay, so we're going to get the volume of a sphere, and your book has a nice picture of a sphere, but you know what a beach ball looks like. So the volume of a sphere that has a radius of 10 centimeters. So here's the radius, but if we were going to enclose it in a cylinder, so here what we're going to do is we're going to take a cylinder that's going to exactly enclose, and then we're going to, it's got to enclose it, and then we're going to stop the cylinder right at the top of the ball. So since this is a 10 radius, wouldn't it be another 10 over here to get all the way across? And then if we're measuring the height of the ball down from the top of the cylinder to the bottom, isn't that also going to be 20 centimeters? So what we're going to do is we have a circular base that has a radius 10. This circular base looks like this. And the height of this cylinder is 20 centimeters, because from here to here is 20 since the radius is 10. So now we're going to find this area multiplied by this height to get the volume of the cylinder. And then we're going to take 2/3 of that to get the volume of the sphere. So the area of this one is pi r squared. We've already done this one. 10 squared is 100, so we have 3.14, which is our pi estimate, times 100 is 314. And this one is in centimeters, so this is centimeters. This was area, right? Centimeters squared. That's the area of the base, times the height. So we're going to multiply this times this. So we get the volume of the cylinder is 314 times 20 centimeter cube, because it's volume. And so this is going to be 6280 when I multiply all that together. Centimeters cubed is the volume of the whole cylinder. And then to find the volume of the sphere, which is inside the cylinder, is going to be 2/3 of this. So we're going to have volume of the sphere is 2/3 of this. So 6280, and the volume will still be in cubic centimeters. So now let's think. 6 plus 2 is 8 plus 8 is 16. That's not going to divide by 3 evenly, is it? We're going to have to go and do it on the board. Now, it really doesn't matter whether I take 6,280 and divide it by 3 and then multiply by 2, or whether I take 6,280 and multiply it by 2 and then divide it by 3. Won't I get the same answer either way? So I'm going to divide it first because I like to keep things smaller. So we're going to say 3 into 6 is 2. 2 times 3 is 6. 3 into 2 goes 0 times. 0 times 3 is 0. 3 into 28 is going to go 8 times. 8 times, 9 times, excuse me. 9 times. 9 times 3 is 27. 1, 0. 3 into 10 goes 3 times. 3 times 3 is 9. And I have 1 left over, so that's going to be 1/3. So now I divided by 3, I have to multiply by 2, because remember it's 2/3 of the volume of the cylinder. So now we multiply this by 2, and I get 2093 and 1/3 times 2. Okay, so now 1/3 times 2 is just going to be 2/3. That's easy. 3 times 2 is going to be 6. 9 times 2 is going to be 18. 0 times 2 is 0, but then I have the 1 to carry. 2 times 2 is 4. So I get that answer. So the volume of the sphere is 4,186 and 2/3. Let's recap this. Okay, we were told to find the volume of a sphere with a radius of 10 centimeters. We showed the sphere being enclosed in a cylinder. So the sphere is 2/3 the volume of the enclosing cylinder. So the cylinder has to exactly enclose the sphere. So since the sphere has a radius of 10, it has a diameter of 20. And since it's the same all the way around, this cylinder has to have a height of 20. So the area of the base of the cylinder is going to be pi r squared, or 100 times 3.14, which is 314 centimeters squared. Then to find the volume of the cylinder, I take the area of the base times the height. So I take the 314 centimeters squared times the 20 centimeters, and I get 6,280 centimeters cubed. And now I have to go off and do the math to find 2/3 of that. 2/3 of that will be the volume of my sphere. So then I went and did 2/3 of 6,280, which I did right here. First, I divided by 3, and then I multiplied by 2, which gives me 2/3 of what I started with. So 4,186 2/3 is the volume of the sphere.